welcome. We have a pretty packed day today. Variety of different things, including you get to find out just how thick your hair is. Okay? Using lasers. So that's the exciting part of it too. Okay. So before we go into that, let's just refresh ourselves here. We talked last Monday about light sources. You guys remember we talked about a variety of different light sources and some of their characteristics. Okay? What we're going to do today is I'm going to start with a brief introduction of light-matter interactions. Then you're going to get a chance to do your hair. Here's the outline. Basics of light-matter interaction. You're going to measure your hair thickness. And this is the data that you will need for your first laboratory report, okay, which will be due a week from today. So I've given you some handouts. Make sure you get the handouts that are there on the back of the room, because those explain to you all kinds of things about doing reports. I will talk to you about that after we do the hair measurements, so you'll get some more information about that. Then we're going to go into light interacting with tissue, what kinds of things can happen, and the effects that laser light can have when it interacts with tissue. So specifics of laser light. Okay? So let's start out with basics of light-matter interaction. We know that when an incoming photon hits some material, what kinds of things can happen? It can be absorbed. Reflected. Pass through. Yeah. And any variations in how it could pass through? It could be deflected. Yeah. These are the basic things. You guys have come up with the basics. I mean, absorption leads to all kinds of other behaviors, because when a photon is absorbed, lots of different things can happen. But we'll focus on that a little bit later. So, interaction of light with matter. Okay? So we know that basically reflection is the return of radiation by a surface without a change in wavelength. Okay? So if I come here and I hit that wall, you notice that it gets reflected. Now, this material isn't perfectly smooth, so it does this kind of specular reflection. But basically, I can also reflect off of another surface. Come on, laser. You can do it. It's a little bit harder to see reflection off of this because this is really meant to show you some other things. But the beam goes in, hits this, and reflects off. Right? So reflection is what you're used to. When you look into the mirror, that's what's happening. Right? Photons that hit you are bouncing off of you, hitting the mirror, bouncing off the mirror, coming back. And the big thing about that is that the angle of incidence is equal to the angle of reflection. Okay? You guys probably all studied that. You've learned that through all kinds of different ways of using mirrors, as periscopes, as all kinds of different things. Pretty standard. Now, you can also have transmission. A photon can just come into the material, like water, glass, or plastic, and the majority of the photons go through. When we look through a window, the majority of photons just go through that glass and come to our eye, okay, with minimal change. Now, not all of the photons come through. Some photons are stopped. We don't necessarily know that. We can't tell that. Like even in your car, it appears like all the rays of the photons are coming through the glass. But in reality, some of them are getting stuck behind. They're getting absorbed or reflected. But for us, it seems like most of it comes through. And then we have refraction. Now, refraction is basically the light has a certain speed in air, right? But when it hits a medium that's denser than air, the light slows down. Okay? The photons slow down. And then when it comes out the other end and it's back in air, it speeds up again. So when light goes into anything denser than the medium it started from, it slows down. That slowing down, if the light came into the medium at an angle, translates into the light being bent. Okay? It bends towards the normal. So it comes in, let's say this is air and this is glass, and this is the surface, the interface. It comes in and bends. And it bends towards the normal. If this is the denser material, the light bends towards the normal. If this was the less dense material, it would bend away from the normal. The normal being a line that's perpendicular to the surface interface. Now let me show you that practically. here I have a block of plexiglass. Okay, it's denser than air. All right. Put it here. And if I shine the laser through it, I didn't work. If I shine the laser through it, come on. It goes straight through, right? Now, you don't know that, but as I go through this block, the light in the block has slowed down and then sped up as it comes back out. Now, if I start going at an angle, can you see what's happening? The angle of this is coming in to here. The light is bent towards the normal. This is the normal line going here perpendicular to this interface. You guys notice that it's bent, and then when it goes out, it goes away from the normal? That's because of it slowing down and speeding up. As it slows down, the first photons that entered into this plexiglass slowed down and didn't go as far. So overall, the whole train of photons basically bent inwards towards the normal. So then when they come back out here, the first photons to sneak out got to go really fast again. Because they got to speed up, they got to bend away from the normal. Okay? And you can see all kinds of different things happen simultaneously in this piece of plexiglass. Here I've got reflection. Here I've got refraction. Here I've got an internal reflection. Okay? And this is what tends to happen in most situations that we interact with in biophotonics. The moment you introduce either lenses, filters, different things, all of this different stuff happens. And in biological tissues, it gets to be a real mess. Okay? Because there's all kinds of little things happening, which we'll be talking about soon. Okay? So, for example, diamond is 2.4, refractive index of 2.4. What that means is that compared to air, which has a refractive index of basically 1, it means that the light is slowed down 2.4 times compared to the speed of light in air. Glass is usually about 1.5. Okay? It depends what type of glass you have. Okay? But effectively, it changes, it looks to us like it's bending. This is the reason why when you're looking at something underwater, okay, you actually think it's in a different spot than it really is. And this is part of the reason why, I don't know if you've ever gone spearfishing, but people that go spearfishing, they have to learn that that's an illusion, and it depends on how deep the fish is in the water. When they go to throw that spear, they often miss when they're first learning because the fish is not where it appears it is. The light has been bent from the fish towards the normal, so the fish is actually further away and up closer to the surface than you think. Okay? And it also leads to a distortion in size. Okay? So lots of different things like that happen. So there are some tools. I just showed you an example of how the light bends, and we can use this, for example, in something like this. This is my representation of a rod, of a tube. You can use the fact that the light will bend to make things bounce and come out the other end. If I had a really long one of these, I can make the light bounce so it comes out the other end. And fiber optics work this way. You'll be learning more about these, but fiber optics allow me to take the light and bend it in all kinds of different directions because of these little internal reflections that happen. Okay? And you'll notice that at some point, okay, come on. So here it goes through, 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 here it goes through. At some point, a lot of the light ends up reflecting off. Not as much light ends up going through. So depending on the angle at which you're coming into the material, you might lose most of the light into reflection rather than actually going through the material. But there's always a little bit that leaks through. Now there's an applet, if you guys want to play with this, with the different substances. It'll be, this is the URL for it right here, just to show you what it looks like. It's right here. You can take your beam in air and you move it, and you see it shows you, depending on the angle that you put it in, it shows you the the reflection and the refraction into the material. And you can change the material. You can say, I want my second material to be quartz glass. You see that bent it more. I want it to be diamond. That bends it the most. Okay, so if you guys want to try it, you can follow that link. Okay. And then we have scattering. Scattering now is a really common one that happens in biological tissues. Basically, it's the light can scatter to the side, forward scatter, back scatter. You can think of it as there being thousands of little tiny mirrors in this material, and they're all pointed in different directions. That's one way you can think about it. Okay? And they're scattering the light. The sky is blue because molecules in the air preferentially scatter blue light. So we see more of the blue light, okay, compared to the other light. And the size of the wavelength compared to the size of the particle determines what types of scattering happens. Rayleigh scattering, Mie scattering, there's all kinds of different types of scattering that have slightly different properties depending on the relationship between the wavelength, the light, and the size of the particle. Okay? Now, what do you guys think would happen to a wave that interacts with a slit or a hole in the material in front of it? So you've got a laser or any other type of light that you like now interacts with a slit. It diffracts. And what does that mean?
It means that
it spreads out an interesting pattern. Okay. Okay.
Depending on what source it is.
Believe it or not, the pattern that you get from a slit versus the pattern that you get from an object that's the same size of the slit by itself is pretty much the same pattern. So whether I shoot a laser at a hair or a hole the size of a hair, I get the same pattern. All right? Seems kind of strange, but light, because it's acting like a wave, think of it what you know of waves. Think of it if there was a wave of water coming this way, or a whole bunch of waves of water. What would they do to that hole? Would they go through the hole? And would you see any waves on the edges of the walls? You kind of see this cylindrical pattern coming out the hole. The waves would go like this, the wave fronts. Okay? With this, the waves would go around, and they would form a very similar pattern. They would be slowed down in the middle and sped up on the sides. I know you all want to try it with a water table now. Did any of you get to do that in high school? Did you get to actually have big water tables where you put stuff in it? You raise your hands if you got to do that? Okay. So a few of you got to do that. That's a nice way to figure it out. There's lots of movies out on the net too that show you. But let me show you an example. So what I have here, I'm going to show you an example of scattering and an example of diffraction. And then you guys are going to do your own diffraction. So what I have here is a cup, plastic cup, and I have a piece of tape. Okay? Tape is a very good medium for scattering light. So I have my laser. If I put my laser to the regular part of the cup, we get to see some scattering. You see those little fuzzy bits right there? If I go through the tape, see what happened? That's a good scattering medium. Okay? Notice what happened? It scattered it just all over the place. It almost looks like the night sky. Okay? Now, I also have a hair in here. I don't know whose hair, but someone's hair. And the hair, I'm going to shine this laser right on the hair. You're going to see a pattern. Then I'm going to ask you, is the hair horizontal or vertical? Okay? So let me see. Probably the best I can do is scatter it in the back of the room. We'll get the biggest pattern. Let's see. There it is. I'm shining the laser directly on the hair. You guys see a pattern? Yeah. You see bright and then dark, bright, dark. See that variation? Okay, so which way is the hair?
Vertical.
Okay, how many of you think it's vertical? Raise your hand. Some of you said vertical, so now how many of you think it's horizontal? Yeah, it's horizontal. Okay. Here we go. I'm going to put it now vertically. It's hard to find the hair sometime. And there it is. And there's the pattern. Now, believe it or not, that pattern, the dimensions of where the dark spots are is going to vary based on two things. Can anyone think of what might change the spacing of that pattern?
The thickness of the hair and how far from the hair is going to start.
Those are thickness of the hair is going to change that pattern, and the distance is going to make the pattern more spread out. And then there's one other thing, the color that I actually use. Because different size waves, different wavelengths, will lead to subtraction and addition at different distances. Now, these are some different things that try to give you a sense of what's happening. And most of the examples they show you are through a slit, but it's the same thing as a hair. So here's a slit, here's the wave fronts coming through, and believe it or not, when a wave comes to the edge here, it's actually going in there's waves going in all different directions. So this is the funny thing about photons. That's kind of hard to understand sometimes. But at any given point here, there's waves that are going straight through, and then there's waves going in all other directions. Those waves going in all the other directions, coming from different locations in the slit, will either sum with each other and make a bright spot, or they will partially negate each other and make a weaker spot, or they will completely negate each other and make a dark spot. So you get this pattern here represented in these waves. This is representing the really bright spot that you saw in the center. This is representing a dark spot. This is where the majority of waves subtract with each other. And that relates to the size of the wavelength and the size of this opening. So those two things together dictate where the waves are going to add up to 0 and where the waves are going to add up to more. Okay? And so you end up getting a pattern that's really bright, dark, somewhat bright, dark, somewhat bright, dark, somewhat bright, dark. Okay? You get a whole bunch of these different patterns. And there's some links here that show you all kinds of different virtual experiments that you can do. But I want you guys to do it for real. Okay? That's why we're going to do it with your hair. Okay? There's also some other ones here that allow you to change the wavelength of the light, and allow you to change the size of the aperture, and see what happens to the intensity distribution, or the pattern that you would get on a flat surface. Okay? And that one, just to show you real briefly, because I did load that one up. There's an interactive Java tutorial that you can load up. And there it is, and you can change the wavelength, and you can see how the pattern changes. And you can change the size of the slit, and you can see how the pattern changes. Okay? You guys can try that on your own time and see what you think. But now, let's go back. Where is it? Okay? So, the other thing that you guys mentioned that can happen, we looked at reflection. We looked at just passing through transmittance. We looked at refraction, so slowing down and bending of light. We looked at diffraction. And the last one was absorption. You guys mentioned absorption. Okay? And in absorption, basically, the light, you lose a certain amount of light as it goes through material, and it does something else. It converts into something else. Okay? That's what's happening. So with that said, now we're going to break up into groups. We're going to need 6 groups, 4 people each. Okay? And let me tell you what you're going to do. There's a packet here for each group of 4. It comes with a handy-dandy, all-purpose logo, a Lego adjustable laser holder. Okay? You guys can modify it if needed. It comes with a handy-dandy holder. And it comes with 4 of these wonderfully crafted pieces of paper to cut up. That you're going to take your hair, stretch it across this, tape it, label it. You're walking around me, label it so you know whose hair it is. Okay? Then you're going to put them in these holders. And basically, you're going to shine your razor in a very precise way. There's no hair there, so it's really long. But you're going to shine it, and you're going to measure a pattern. And that pattern, you're welcome to take as many as you want. I made you rulers. Okay? then you can write down where the dark spots are. It's really important to know what the dark spots are. You can line up the bright spot with the center, okay, on these rulers, and then you measure the dark spot. And I've given you a little thing here that says trial number, laser wavelength, distance from here, okay? There's going to be a couple of really important variables. You're going to want to be a certain specific distance away from the wall. I recommend you figure out a distance in meters. In the end, you're going to be working with metric units all okay? So there's some things I'll show you on the equation up there in a second. But you're going to want to get yourself a distance, usually 2 meters is best. Okay? And I've got some big measures. Unfortunately, they're inches, but I have a little handy conversion. 78.74 inches is 2 meters. Right? You have an ASCII tape, which I recommend you use for figuring out exactly where the 2 meters is, so you have that labeled, and you can use that. And what I've seen people do in the past that's worked well, some people have some leftover sheets there, years past. People will take their sheets. This is the first year you guys get the handy-dandy rulers, frequency rulers. This is a really nice addition here because you're like using it. But what you do is you basically tape the thing to the wall where it's going to be needed. I wouldn't use a whole bunch of these tape because you can move that. But it's going to be fine. And then you measure your hair. You measure your hair, and your hair, your hair. Or you measure your hair with the red laser and the green laser. Your hair, red laser, green laser. That's the data you're going to need. You're going to need to have the data of the pattern and the dimensions of the pattern with the red laser and with the green laser. Okay? Because then you're going to have to use this calculation that we have here to figure out your hair thickness. Then you're going to have to report to me your measurements. And you guys are going to be writing lab reports. You each write your own individual lab reports, but it includes the data of all 4 of your lab members. Okay? I'll talk a little more about lab reports after you guys have some time to actually do this part. Any questions about this part? Let me show you here what you're doing. So, this is a diagram. Here's your laser. Here's your hair. Okay? The distance from your hair to the pattern on the wall is the distance L. Okay? Angle, so you see this is the bright spot. See, this is the center point. This is the really bright spot. Then there's a minima, a dark spot, a bright spot, a dark spot. What you need to measure are, you need to make sure that the center is at the center of that ruler. Then you need to measure where all the minima are. Minima 1, minima 2, minima 3. Ideally, if you can measure 3 minima, that would be good. You can also go further if you like, but you want to try. And it looks kind of like this. Bright spot, minima. Bright spot, minima. Bright spot, minima. M equals 1, M equals 2, M equals 3. Okay? And this is your equation. The thickness of your hair times the sine of this angle right here, the angle between the center and the minima, is equal to whichever minima you picked, because you could pick minima 2 and then it would be that angle, times the wavelength of the light you used. Now, look on these lasers and try to figure out the wavelength. If you can't, let me know and I'll come and tell you. They're all pretty much the same. All the green ones and all the red ones are pretty much the same. And you can do the measurement of your hair thickness at M equals 1, at M equals 2, at M equals 3, any one of those, and that's one of the things that you can try to see if you get different answers. Okay? So, with that said, I'm going to turn the lights on so you guys can get your material and get your distance set up, get your spot on the wall that you want to use. Okay? The green lasers are going to be easier to see more minima because they're brighter. The red laser is going to be weaker, okay? But you should still be able to do it. And I have 2 supercharged lasers that will be brighter, and I may bring those around if you guys want to try those. Okay? Questions? We're going to have about 45 minutes for this section. So you have to get your measurements. You've got to get both colors with each of your hairs. And this is where it's important to keep good notes, right? Remember, you're writing a lab report. And that lab report has to tell me the procedure, how you went about doing this. It has to have the details of your procedure. I know that many of you may not be familiar with writing a lab report that is open-ended in nature. Okay? But this is going to be your experience. That's what we're doing this for, actually. And we go through a long process with this one to get it just right, so then when you do the second one, you have a lot more knowledge about how to do these. Okay? But it's going to be your responsibility to look at those sheets that I gave you, look through them, especially the checklist. You can imagine a checklist kind of says it's a checklist. That's what we look for. If you don't have the items in the checklist, then something is missing in your report. Okay? But again, you're going to be handing in individual reports, but of the work of the team. So you can share it. Of course, you share the data. The data is going to look the same, but you may choose to interpret it differently.
So we have to have our data plus the other people's data on our lab report?
Your lab report has to have the data of your whole group. Okay? Now, the other thing I'm going to do in the meantime is I'm going to pass out the sign-up sheet for today, but there's something different about this sign-up sheet. It has your magic code number. Okay? Write that number somewhere, and I'll tell you why later. Because what you have to turn in cannot have your name on it. Because we have to do what's called anonymous peer review, and we're going to be using the code. Okay? So make sure when you sign in, you read what your code is and you write it down somewhere. Okay, so go ahead and grab your things, start plucking your hairs, and start getting them on there. Make sure you got teams of 4 first.
Sure.
Feel free to find spots in the wall.
What's the one with no hair? What their hair looks like?
Remember, keep track of details. Keep track of details. If you know you have hair products on today, if you know your hair is dyed, whatever it is, keep track of the details.
Oh, I got hair.
If you end up using a beard hair or chest hair, keep track of that.
My hair's not going to stretch across the top.
That's going to be
If you happen to have particularly short hair, then have some of these that have slightly smaller openings.
I think my beard is long enough to do whatever.
Pick your material and pick your spot. There's one station that doesn't have a green laser. I'll give you the green laser. You guys can grab multiples of these if you want. Feel free to grab multiple sheets of the ruler if you want, whatever you like. However you want to do it.
There's 6 of them.
There's 6 of them, but you guys need to do 2 measurements each. So you need at least 2 of the ruler sheets. 1 won't be enough.
I like my hair's going to stretch across the
It will.
on the top. On the sides.
Make sure you remember whose hand is who. Okay, there's one group that only got 1 laser. Where's the group that only has 1 laser?
We only have one.
Okay, I'll bring it up. So there's 6 of them. This one is big, guys. So.
Look at that.
There's none of that.
Use those.
Putting the laser back together?
I know.
Yes.
When doesn't your phone?
Yes.
I just have to make sure it hits it.
Yeah. When is that short?
As long as it's some point on there. I don't think it has to.
I don't care.
Alright, if you don't need the tape, then
I don't need it.
we could have two going at once. Because there's a red one in here, and we got plenty of
And if you happen to be particularly quick, I'll let you try the blue laser.
Where are the yardsticks?
All we have is 2 measuring tapes. So he's got one of them right there.
Well, I guess it should be a double.
And remember, you're measuring the distance from the hair to the wall.
Yeah, okay, so it's gonna hit the hair. Did someone shine the laser?
You're gonna want to you guys need to make sure you tape down onto the ground, onto the table, your hair holder. Okay? Because you don't want that to move. Because if that moves, your distance has changed. It's good, Don. Okay, you guys are missing a red laser, right? Let me bring you a red laser. Okay.
Straight down.
We gotta take the hair has to be there. So we have to do that. Okay, now, where's the stand?
This area.
Remember, what matters is the distance of the hair to the wall, not the distance of the laser to the wall.
I didn't
That has to be fixed. I want that to change.
You guys need ours,
There's only 2 measuring tapes that have to go, that are going around. Make sure you have some of these sheets to use. You guys have some of these? We also have 2 of these holders. I prefer this style holder and the laser.
It all depends on where you tape your hair into the. Oh,
We also have scissors to cut your hair if you don't want to pull.
we have to take down the laser. When is that 0? Good. Great. Well, we can always move this. Okay, yeah, just line it up with this
You guys getting there? You got the distance?
Oh, we need to wait for a tape measure.
Okay.
Yes, our hair.
You can go 2 meters, 3 meters, whatever you want. We're gonna turn off the light shortly.
Oh, he's not. You might need to turn off. It looks like it's changing. Yeah, oh yeah, yeah. Except it's, oh, it's horizontal, so we have to make this. Right again. Well, I think that might be a good idea. That's good. Alright, we got
I'm gonna write on a different table.
or we, I guess we don't necessarily have to do that. Might help though. I'd tip it. Tip it? Alright, press it. Right, yeah, so I can barely see the time. Well, when he turns up the light, yeah, but I can still see it. Oh, yeah. Right. So I can see it too. Okay. Watch. Use the table as a guide.
Has everyone measured their distance from the wall? Okay.
Is that level with the
39 patterns.
2 meters?
You guys see the pattern?
I feel like there's like 6
And, you know, draw on those rulers, guys. Draw your pattern on the rulers. That's why I made those in paper so you guys could draw on them.
Yeah, the front of the table is pretty.
Can you see it?
Be really careful. Don't point the laser in your eyes.
Okay.
This is too just your answer.
Anyone still measuring? You guys are still measuring, okay. Then we're going to turn off the lights so you guys can see this really well.
78.74.
Remember, as you're keeping track of your procedure, the procedure has to have enough information so that what you're doing could be replicated by someone else who wasn't here. Okay? Did you guys hear that? Your procedure has to have enough information so that somebody could replicate it.
The green will be changed. Should we measure how far these are? So that. Fire the laser. No, that's 2 meters. Yeah, 2 meters. Oh, and then we just want
We don't need it. We can take lighter. What are we?
Okay, everyone measure zero. I'm going to turn off the lights. Be really careful not to have the laser shine in your eyes, especially after you're marking.
Yes, we know that makes sense, maybe.
The green here. You can mark the green as 5:42 and the red as 6:54.
No, it seems like
Oh, yeah.
Get it on the center there.
You mark the minimum, the center of the minimum.
That's good. Let's see.
You're marking the center of the minimum.
Should you put the laser closer to the
Oh, that's a good one.
That might help.
If you're not on center, you can also say this is the center and these are the minimums. You can always remember. Just a little harder. Remember, if your center is immediately
Yeah, we
on,
can always
exactly
mark
like
the spaces and then you can see that.
Okay, that's good.
if you're not exactly centered, you can still mark it where the center is and where the other ones
We
are.
only get like 3 on each side.
Okay. Let's do a little bit again.
Is that good? Yeah, and you can just do one side. Are we done?
Okay, just do one side?
No. Are we done with this later?
Yes.
Here's the green light.
Right, negative green.
So I'll give this look in there.
The distance between the hair and the laser does not matter. It's up to you guys how you want to do that. Yeah, you can redo the center. If you mark where the center is, you can always recalculate.
Wow, that's good.
Do we need to know the distance of the laser from here to here? No, it shouldn't matter. Well, I mean, it'll
This is from the laser to the hair.
If you look at the paper, I mean, like, it just says the laser is right there.
Yeah, the laser doesn't matter. No, yeah, we can. Sorry.
You don't necessarily have to do that. You don't want to, but
All right.
I don't think so. The tape's off center and all that. Yeah, it could be hitting our tape. Look, the tape's not too bad. It is a little bit, from my perspective, but it would be more off to the left. Concentrated scatter on the left. Action shot.
nice pattern.
Yeah, like us catching the laser. Yeah.
I know. That's something you have to just mark.
Would it help if you like clean the cover?
This part is like, these don't come out. There's something there. Try to get some mustard laser if you want, or you can just.
Why are you moving it?
Remember, if the laser isn't perfect, it's not perfect. But you need to mark what's going on.
So,
Laser is ready.
Alright. You can put that Lego back on.
You go get some new
I
batteries.
think you missed a little bit.
should be the exact same distance.
Your sacrifice will not be forgotten.
Bravo, 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 bravo.
Okay, good. Okay. Alright, Sam, green. Why do people It's a very interesting show.
And you read your papers. Red. Oh, you did green.
Should be the same one.
Yeah, it's too hard to read over there.
Great guys.
Those are big, yeah, Ryan, turn them off. Alright.
We didn't have to.
We didn't touch it.
The green is 5:30.
Right now we'll
There's one more ready.
Before you took it all apart, it's fine. It's active by itself.
Yeah, that's really good.
I think nothing.
You could be like, well,
We probably don't know.
It's like 100. Two hairs down. Green.
I'm trying to see this in there.
You said green with 530. And then red was 60.
That's a good one.
And then van was small.
Yeah. It's almost easier to see on the blue than on the Where's that sitting?
did you go?
Oh, nice.
Yeah, we have to do another try with green.
Are you guys have so much scattering in red? Is it a problem that it has that much? Huh? Is it a problem that it has that much scattering? As long as
Look at that.
but
It's kind of smaller.
guys, is it all the time?
I can't find the pattern.
I can see that.
Pretty good sign, right?
Right.
Actually, you said if we have time.
Come on.
doing the laser.
Know where you're marking.
Which one trial of each? Very scary.
Any group is done and wants to try the blue laser, they're welcome to try the blue laser.
Oh yeah, what's still see the man. Alright, here's the medium.
Oh, right, because it's try one with the red. Try two with the red.
I think four was it? Yep.
Someone's got volumizing condition.
I bet you. I bet you.
Is that good?
I closed my eyes and I see the cracking pattern.
You could, yeah, just divide and then plug that in. You obviously see like two engineers.
Move the laser.
Alright.
I'm moving the laser.
Let's see the height. It's the minimum. What? Oh.
Okay. So basically, the A is the thickness.
We don't. Oh yeah, you could just find the hypotenuse. But then no, but you have to find the angle.
So you wonder what the difference
But can't you just do the ratio between x and the hypotenuse because that equals sine theta? You can plug that in.
Yeah, you could. Yeah. You don't necessarily need to find it.
Oh, okay, so it was just like a whole right?
Okay, guys. One thing, I've never gotten a picture of the blue laser.
Apparently this is kind of finicky, so we have to work quickly and
I'm gonna get a picture of it, you guys do.
Seriously?
It's not like there's a pattern.
Yep.
I saw it and it's gone. Yeah. All guys, try the want to try it? Yeah, I was gonna say.
How are you guys doing? Check out your measurements?
That's mine.
Okay, good.
I didn't start it
like right here.
What? How much time?
Yeah, you could use work on it. Yeah, Sandy can figure out the theta using tan theta equals x.
You just plug it in the side.
Well, we have to calculate. Or he wanted us to take.
What?
Wait,
I don't understand M. M is M.
It's just no. If you do like M is just me 1 or 2 or 3 or 4.
Oh yeah.
And then
Let's try more hair.
okay. This is James. Yes. This is the James hair.
So for n, you just write that it's minimum. It's minimum one. You just
Yeah,
write
you try one thing. And then the wavelength.
Actually, that's what I'm
And then we just do the ratio of XL to find the mean theta, the arcane of XL. And then you put sine theta.
Lambda's the wavelength. Lambda's the wavelength. It's minimum times the wavelength.
Yeah.
I do enjoy it.
Divided by sine. Whatever, and then you figure it out.
Yeah, so if you like, if you didn't want to like solve anything, I guess you could do n times wavelength over sine arctangent x over L.
Yeah.
I end up watching the show later.
So I would give it
It's a pretty simple law.
I'm getting like a laser or whatever.
I remember they done something.
Oh, they have the blue laser? Oh, yeah.
It's tricky because like
I can see it.
Most.
there's something where it's in, but it's like at the half mark, but I could convert it like right in there, but I could just the laser's kind of giving out.
Close my eyes.
There's the back door.
Okay, it starts out strong, but then it dies.
Yeah, we're gonna have to work fast once we get the measurement. Maybe like cool down.
It's super fast.
Yeah.
Yeah, Could wave that thing everywhere.
Let's give it a try.
It's the last one. Yes. It's like everyone got blue except for one.
Okay.
Here.
We're working good?
Yeah, we just cut out on us a little bit. We ran the development back. We're trying to get the last scare.
Alright, that should be sufficient. Anymore.
Okay, if you guys have all the measurements, try to figure out. Try to do the math. If you have a calculator. The blue is very
Somebody wants to try the blue.
See if you can make any sense of it.
What are we measuring this thing?
It's from the center to the first one.
Oh, 470. It's so much weaker.
Yeah, the blue's really weak. You're not going to see a very strong.
Why is it so
Yeah, we
The distance to the first minimum.
Yeah.
This is
values and sensitive.
Who was that? It should. That was try this green one. So we get the same thing. They're the wavelength is 532 and what's the benefit? Like, what's the benefit of using?
Oh yeah, you should get the same thing with the X. The X and the.
That's your application. Are you getting it all? You guys are meant to make do with what you have. You'll be fine. If you've done taking your measurements, try to do a calculation on one wavelength and one person's hair, just to make sure that you know the calculation. So don't have questions, okay? Try it. Try doing the calculation on one trial. Try figuring out what size hair you have.
So if you put it 2 per meters and then nanometers next to it.
Nope.
Yeah, they're doing it and it's not doing it.
No, not trying to.
Either way works.
We should. Oh no, we should have nanometers because the hair is going to burn. So 2
Micrometers or meters?
So many conversions.
And you know what? 10.5 millimeters means 5 times 10 to actually it's like 12.6. I think their first 3 and then
We should figure out the distance between each minimum so 60.
It's not enough. It's not enough.
just looking at this first one.
It's how many nanometers it is. 6 and 8 nanometers.
Okay, the blue laser's back online.
Alright, so what was the second one?
I mean, just high.
Yep, 5 minutes.
Our close side, so it gave me like the same number. But it can be vector. Alright. These numbers are a little bit different.
How different?
Well, it should be the same. The hair length line should be the same.
Guys. Oh yeah, you're
I think there's like
I've been on camera.
If we wanted, we could redo that as a 30 minutes. In fact, let's do that.
Wait, let me calculate everybody. You guys are doing Hey, if they play that thing down, that conversation's being recorded right now. But if that thing's played, like what we're talking about, they come back loop and they do like 30 minutes.
Everyone made all the measurements?
And the speakers, so like the voice is right there, like
We're trying to redo one.
You get that when you talk on the microphone, and your speakers are on loud, right? You turn yourself on there. Yeah.
Oh, there it is. The center. Let's just from the center to go to.
So the width right there can be the same for all reasons. The
Well, I guess we may take this
Measurement. You guys get a measurement? Did you try doing one of the calculations? You try doing one of your calculations?
Yeah.
What'd you get?
It was close.
Close to what?
Well, we compared the two wavelengths, and they were close to each other.
That's the right ballpark. So you're doing
Nice in the ballpark. Did you want to reuse the squares?
Yes, please. Cut out your hair. I need to reuse those little squares, so just cut off your hair off of it when you're done. There's some scissors up here. Don't worry about your name being on there. Okay, 2 minutes and we're going to start talking again. It's just hair. It's fine. Somebody 10 years from now will figure out exactly what we're doing. That's scary. Okay. I basically try to do the measurement, try to do one set of calculations.
Yeah, I guess you're close
until you pay enough weight.
It has to be small.
Make sure you sign up and get your secret rules.
Oh, it's 6:15.
You guys got some numbers? Did you get some numbers? You're there. As long as one person knows how to do it and getting a reasonable number, that's okay. As long as we're not getting meters or centimeters or nanometers.
So wait, nanometers are.
Oh, you did this.
That's why you should be there for that. Are we gonna set up a template? Probably do at least nanometers How many, like, regular thing big, like 1.2 or 100?
I like this better.
We got 1.2.
Okay, guys, let's all get back to our seats, please.
Why is it 30,000?
Please go back to your seat. You're welcome to put the Lego stuff and everything back up on those tables. You get to keep those rulers. So you know.
Yeah. You know, he's like 30,000 one time. It could have
That's why we did it.
Yeah, it could be.
Right? The idea is like, right?
I hope everyone has written down this equation. Good, good. I will put Monday and today's lecture online about later today or tomorrow at the latest. So you guys can always access it. Okay? So I've heard a variety of different measurements that you guys have calculated. I've heard anywhere from 60 micrometers to 150 micrometers. Those are all reasonable ranges of hair sizes. You shouldn't be in the nanometer range. You shouldn't be in the centimeter range. Okay, you know it's smaller than a millimeter, and so it's somewhere in that range. You can be as low as 30, it can be as high as 300-400. It really depends on your own hair. Okay, now, some important things to think about for the report that is due next week. Okay, next week this is due. Your first draft is due next week. What are we going to do with that? Well, you've gotten 3 handouts. Probably the most important handout is your checklist. If you have all the items in your checklist, you're much more likely to be in good shape, right? If you're missing half the items in the checklist, you're likely to be in trouble, okay? The one longer sheet kind of explains the elements of the checklist. That's kind of what that does. And the one about graphs is just something for you guys to think about if you are going to create any graphs for this particular laboratory. Now, I have to tell you, you may not need a graph for this lab. A table might be perfect for this lab. So don't create gratuitous items if not needed. You think about it depending on what kind of data you want to represent and how you want to represent it. Now, you're going to need your code, so make sure, is everyone signed in, the attendance? Make sure you keep your code, okay? That code, what you turn in next week, you're going to hand in 4 copies of your lab report, okay, on paper. You're also going to email me the electronic version, okay? But you're not going to put your name or your partner's names on there, okay? What you are going to do, well, ideally the one that you send me, the electronic version you send me, would have a cover sheet with all of your partner's names on it. That would be useful, okay? That would be a good thing. But the one that you're going to give, the other ones that you're going to hand out to others, the paper ones, only have your number on it. So if you were number 6, you put number 6. And then what's going to happen is you're going to hand in all the copies at the beginning, your copies, and then we're going to spread them out among 3 of your peers. And if your secret code was number 6, you will pick up 7, 8, and 9. If your secret code was 22, you will pick up 23, 24, and 1. Okay? So you're going to be commenting on your peers' reports. You will have 1 week to put comments on the reports of 3 of your peers, and then you will turn in the whole package to us. We will be both grading your draft and your comments to others. Okay? Then you will all get the comments that your peers have given you, plus the comments from Professor Shackelford and myself. You will have, again, another week to fix up anything, and then turn in the final. Okay? Which will also have a grade. So we go through this process because it gives you a chance to see what other people do, gives you a chance to comment on others, and this is more how science is done. Yes?
So we bring 3 hard copies and just email you the photos?
Yeah, that would work too. You definitely have to bring 3 hard copies. And you have to email me. The one you email me should have your name on it and your partner's names. Okay? Now, just because it's been asked before, I'm going to show you an example of what somebody did last year in terms of reviews. So this was a person was number 6, and this person reviewed 3 other labs, like I told you, and this is what it looked like. So there was their abstract of one of the labs, the introduction, the setup, a table, and conclusion. And then this person also had a whole bunch of tables of numbers. This tables of numbers was overkill. It was way too many, okay? You don't need to have this many. And that was the graph they did. Here was another one, just to show you, this is what they turned in. So a week from now, this is the kind of thing they turned in. Discussion. This was the last one. This one did diagrams drawn by hand, which is fine. Diagrams of setups drawn by hand is no problem. If you don't want to use some other software, you can do it by hand. And that was kind of what it looked like. Okay? The thing you can't see in this copy very well, especially when I print out, there's all kinds of written comments in the margins, which are what you'd be doing to your peers. You're going to be writing all kinds of comments in the margins for them to think about. Okay? So that's an example, just so you guys have a sense of it. Okay? And please email Professor Shackelford or myself if you have any questions. Because you do have 1 week, but Monday we don't have class. Okay? So feel free to ask us any questions via email. We'll respond, and we'll send out anything that looks like it's relevant to everybody. We'll send it out to everybody, to the whole class. Okay? Yes?
Do you want us to have a diagram of what it actually looks like where all the minimums are, or if we just have calculated one from center's minimum stuff?
What I'm going to answer is probably going to be a little disappointing to you, but this is really going to be up to you for you to think about what others might need to better understand your results. So think about it. 3 of your peers are going to see this. Are they going to understand what you did and the types of calculations you did? If you want to represent that by drawing every single one of them out and you think that's the way to do it, let's see what your peers think. In reality, the way it works in science, there are some accepted rules but there's also a lot of opportunity for going outside of those accepted rules that work. So it kind of depends on what you want to do and how your peers and how we perceive it. The point of a laboratory report is to convey what you did and your results, and the kinds of things that might have gone wrong in your results, or the kind of explanations of why there might be variability in your results. Those are the things that are of critical importance. If you are an eloquent writer and can write the whole setup in such a way that it's very clear that it doesn't need a diagram, then don't put a diagram. If you're not very good with words and describing things like a setup, so that somebody else that's never seen it could replicate it, then put a diagram. It's really up to you guys. Okay? Think about significant figures. Okay? When you measured your distance, your 2 meters, how many significant figures did you have in that measurement? I told you it was like, what, 78.17 inches or something, or 78.74 inches. So were you able to measure 78.74 inches? What were you able to measure? 78 3/4. Okay, so that's roughly how many sig figs? I'm hearing 3 to 5. What do you guys think? How good do you think you could get it? I hate inches because they have all these quarters and eighths, and it's just... You told me that you went to 3/4, 0.75. So that would be 4, but realistically, you were probably only 3. Okay? So can you give me a hair measurement of 143.672 micrometers? How many significant figures is that? 6. You're not going to be able to do that, okay? This is a really, really common mistake. You guys just love your calculators. They give you lots of numbers, and so you guys just give me all the numbers. That's not going to work, okay? You're also going to see variability. Some of you took measurements more than once. Some of you might decide to do the calculations with m equals 1, with m equals 2. Those will give you different answers, okay? So there's going to be some variability in your answers. And that's the kind of things that you can convey. In theory, should the answer with the green laser be the same or different that you get with the answer with the red laser? In theory, they should be the same. How many of you think that you will have exactly the same numbers? Okay, it's never happened. Okay, you will have some variability there.
Is that in part because the red laser is 630 to 680, and the green laser is 530?
That can be part of it, though. Most of those lasers have been checked, and they're really close to 654. Okay, so I've checked them with a spectrophotometer that tells me exactly what the wavelength is, and they're very close. The only ones that I haven't ever checked are the 2 ultra bright ones, and I'm going to see if I can check them either today or tomorrow. And if anything's weird about them, I will let people know. Okay? Because those say, I think the red one says it's between 500 and 700 or something. I mean, it's some ridiculous range. And it's not true. But okay? Any questions right now about this? Okay. So you may be frustrated at times with this process, I'll just tell you. But do the best that you can with your first draft, okay? And then you'll get some feedback. Okay. So we now are going back to interaction of light with biomaterials. And we're seeing that, we saw a few minutes earlier, that an incoming photon can interact with something living, and you can get transmission, reflection, refraction, scattering, and absorption. All those different things can happen. Now, what will happen predominantly, what different things might happen, it's all going to depend on the physical and chemical structure of the biomaterial. That kind of makes sense. Whatever the material is made up of and how it's created, how it's made up, will define what are going to be the dominant processes that we see. Okay? Something that's transparent may have a lot of transmission and very limited absorption. Something that's opaque and none of the light goes through, absorption might be the dominant process that's happening. But a little tiny bit of light might get through. Okay, so something to think about when you have a photonic energy interacting with something living, different things can happen, and primarily we can get heat, we can get chemistry, meaning we can get some chemical reaction to happen, something can change, or an orientation of a chemical can change of a molecule. We can get more light coming out. Remember, we can get light that's the same wavelength. We can get light that's been bent. We can get light that's a different wavelength. We can get light based on fluorescence. We can get light based on phosphorescence of the materials. All those different things can happen. And we can also get motion. I can have light interacting with something, and I can use it to trap something or push something, okay, because of the momentum that photons have. Okay? That's the kind of range of things that can happen. So, how do we use these things? Well, we use these things in a variety of different ways. One way in which we use it is we have special microscopes that can use the fact that light is slowed down in materials with different densities to give us, this is an image of this amoeba in a regular light absorption microscope. So in this case, you see that you don't get a lot of detail because the light absorption between water and between the actual parts of the amoeba aren't all that different. So you get very little contrast. But if you look at how the light is slowed down and are able to emphasize the differences in speed of the light as it goes through the material, then you get an image that looks more like this. And these images are characterized very much by these halos whenever you're doing this type of microscopy. And it's called phase microscopy. And this is showing you, when you have incident light, what happens when you have a stained cell, a cell that's been colored to show contrast, is that you get some light absorption. But you're still only looking at where was light absorbed and where was light not absorbed. When you have this type of phase microscope, you can actually see where the light waves came out of phase because some waves that went through the material were slowed down because that material was denser than the medium in which the cell was. So it can exploit those slight variations in speed that cause things to get out of phase, and it can recombine those to then give you contrast. Okay? So this is phase contrast microscopy. This is a way that we look at how light and tissue interact to make it useful for us. We also can do absorption. So basically, absorption and emission molecules are processes by which the materials borrow from or lend energy to the electromagnetic fields to which they are exposed. So the energy is absorbed. If a molecule is in a low energy state, a ground electronic state, it can absorb energy based on other excited electronic states and the vibrational levels. So there's very specific wavelengths that can be absorbed by a given molecule. Okay? And it has to be absorbed, it has to fit one of these quantum jumps that bring it to a different electronic state and or a different vibrational state. And even between these, there's little things called rotational states. Now, the microwave region, I don't know if you remember, but microwaves tend to make molecules rotate. Right? We talked about the waters rotating and hitting each other and increasing the temperature. Infrared radiation can change the way molecules vibrate. Okay? We talked about that too. And as you go to higher energy, UV or visible can change the way electrons are distributed within a molecule, which can lead to a change in the shape of the molecule, or it can lead to bond breaking. Okay? So, you guys ever seen those glasses that are clear when you're inside, you go outside, they get dark? What do you guys think is happening there? Okay, UV rays.
Change the shape of the molecule.
So the energy in the higher part of the spectrum, traditionally in the blue and low UV, actually cause the molecules to change shape. When the molecules change shape, they are in a different conformation that becomes opaque to light. Okay? And therefore, it can, boy, this thing just lost the button. It can make them a little bit dark or very dark, depending on how much UV is hitting those and causing that change of shape. Now, the moment that UV energy is gone, the molecules can naturally go back to their original state and become clear again. Okay? And that's all that is. So, in reality, whenever you see absorptions, it's a combination of electronic, vibrational, and rotational absorptions going on.
Does that process wear down over time? Like, if you have those glasses for a long time, they will stop changing shades as much?
You know, I don't know the specifics of those glasses, but chances are there will be some damage over time, and therefore it will be somewhat hampered. What that lifetime is, you know, I'm sure it's not forever, but it's probably a pretty long time. I don't know the specifics. Okay, so you get that combination of things, and basically you can get vibronic states, which is states that are both a combination of an electronic energy state and a vibrational energy state that basically cause a photochemical reaction. So the light causes a reaction to take place. Okay, typically photochemical reactions result in destruction of the molecule, but they don't have to. This is what we're talking about. A lot of those things can be reversible, but not forever. And excited electronic states can also degrade into different vibrational states, which then can result in heat. So you can absorb light, which then results in heat, generation of heat. Okay? So what does it look like with a typical biological molecule? In a typical biological molecule, you've got a whole bunch of different electronic transitions, and electronic vibrational transitions, and rotational transitions. And what it turns out to is it gives you some kind of spectrum that if here you have increasing energy, and here you have the amount of light absorbed, you get a spectrum that looks kind of fuzzy. So you guys remember when we looked at the fluorescent lights, there were some pretty sharp lines that you saw. And when you looked at the neon flamingo, there were some pretty sharp lines. In most biological materials, there's a whole combination of things, and you're usually in liquids. Gases are the ones that give you those nice straight lines. But whenever you get to something in liquid, there's such a huge combination of electronic and vibrational and rotational ways in which you can absorb energy that what the absorption spectrum ends up looking like is something broad and not nearly as well defined. Okay? Does that make sense? Because when you've got a solid, which also has liquid in it, you've got a lot of different interactions going on. And each of those interactions causes a slight variation in where the specific vibrational changes will be for that set of molecules. So you get a range. You do not get nice, sharp gas spectra. Okay? And there's been an equation that's been made. It's called Beer's law. And some people remember it by the deeper the glass, the darker the brew, the less of the incident light that gets through. There's all kinds of little monikers like this to help you remember. But the basic idea is that this quantity absorption is specific to a particular wavelength, and it's dependent on something, some kind of coefficient, this is called an extinction coefficient, that is specific to that molecule at that wavelength, times the length that the light has to travel through times the concentration of that species. So what this means is that the absorption, if I have a container, a glass container, and I pass light at one end and I measure how much light gets through at the other end, if I have a bigger glass, more light will get absorbed. If I have a smaller glass, less light will get absorbed, right? Less of the material. If the material that's in there, there's more of it, more light will be absorbed. If there's less of it, less light will be absorbed. So this is a way of codifying that, and you can then use this if you know that you're looking at the absorption of iron. You're trying to figure out how much iron is in this solution. And you know the extinction coefficient of iron at a specific wavelength, and you know the size of your container, then you can actually figure out the concentration of that iron oxide in your liquid. Okay? Or of caffeine, or whatever the substance is. If you have some specific wavelength and specific markers, you can figure out concentration. Or if you know the concentration and you know the path length and you know the wavelength that you're using, you can figure out the specific coefficients. There's books that have these extinction coefficients at different wavelengths for all kinds of common substances. So people can look these up and figure out the concentration of something by doing a simple experiment. Right? One that we use all the time with our students, our more advanced undergraduate students, is we do nitrate concentrations or caffeine concentrations. We look at a whole bunch of different foods and measure the amount of nitrates, or we look at a whole bunch of different drinks and measure the amounts of caffeine. You might have done some of those things in high school. Some of you might have tried some of those things, but you can do that through absorption and knowing this information. Just to give you a sense, an absorption of 0 is equal to 0 photons being absorbed. An absorption of 1 is equal to 90% of the photons being absorbed. And that's because of this log function. If this is the incident number of photons and this is how many got through, the log of 10, if 10 times as many photons went in as came out, 10 over 1, the log of 10 is 1. If 99% of the photons were absorbed, the absorption is 2. Okay? They use this log relationship because they realized that then you could figure out an absorption and it would be linear with the path length and with the concentration. So this is Beer's law. I will not ask you to memorize this equation, but just have a sense of if you increase concentration of something, that less light gets through. Okay? So what do absorption spectra look of some interesting molecules that we care about? Well, here's the absorption spectrum of DNA. Right? So here is the relative absorbance, and here's the wavelength from 180 to 300. So this is all in the UV. So DNA absorbs in the UV, and if it's double-stranded, it has this absorption curve. And if it's open, denatured, not double-stranded, single-stranded, it has this absorption curve. So I spent 1.5 years of my graduate career doing that with RNA. I'd get different shapes of RNA, I'd put them inside the instrument, I'd heat it up slowly, I'd see the change in absorption characteristics over a range of wavelengths, and then I could figure out how much of it was together and how much of it was open. And when did that transition happen? And did it go back when I cooled it again? Okay? So the reversibility. And I figured out that I could make a little tiny thing called a hairpin with only 2 base pairs and a loop of 4 around, and it could be a really stable molecule. And actually those things are now turning out to be important as SNRPs or small RNA fragments. Okay? So at that time we didn't know about that. We were just trying to figure out stability of things. But over time it's been figured out that those are really relevant and important because if it's stable at 50 degrees, it's stable in our body at our temperature. Yeah.
I'm sorry, could you say what you did again?
I was taking different combinations of nucleotides that it's a single strand that could come together like this and connect with a hairpin that wasn't connected. And I was trying to figure out how big does this stem have to be to make it stable? How many double pairs? And so I would heat it up. I would look at the absorption at a certain range of wavelengths over a course of temperature changes. And then I would see at some point that the absorbance would change dramatically because I would have gone from the native state to the denatured state. And that happens relatively quickly at a certain temperature, depending on how stable the molecule is. Okay? So you can tell things like that. And here are our visual figments. Remember I told you we only see red, green, and blue? Well, I kind of lied. We see red, green, and blue, and then we see yellow. But the yellow we interpret as black and white. So we interpret as, just light. So here's our red sensor. That's its sensitivity, its absorbance curve. Here's our green sensor. You notice the two overlap a lot. Okay, the red and green sensors overlap a lot. And here's our blue sensor. Then in between here we have another sensor that happens to be in our rods, which is rhodopsin. And rhodopsin is most sensitive to this part of the spectrum. Okay, so the beginning of blue to yellow. Okay, so these are the absorption spectra, the relative absorption spectra of the pigments in our eye. Well, so what would color blindness be? Color. So it's the inability to distinguish between certain colors, and it's very easy to understand now at this point. If I have cones that are specific for red, specific for green, specific for blue, if my concentrations of those are not the standard, then I'm going to have a problem with one of those colors or with a combination of those colors. So if I all of a sudden have way underproduced my green cones in my eye, then I don't sense green very well. And all the combinations with green I don't sense very well. And that leads to color blindness in certain colors.
So can people be just completely colorblind?
I haven't heard of that. I've heard of blue-green color blindness, but I haven't heard of that one. There is? Yeah, I don't know. Yeah, so I guess it does exist. I mean, I've heard of blue-green is relatively not common, but it does happen. You still have, this capability, but again, you wouldn't be seeing much into the red. You have the capability, and you wouldn't be converting it into color. You would be converting it just bright or dark. Okay? So we can match the wavelength. So this is, by the way, the absorption spectrum of water. So you notice that this is a logarithmic scale down here. You notice that water, this is 100, 200, 300 nanometers, so 350. Water does not absorb very much in the visible range. So water does not absorb very much of our visible spectrum. But it does start to absorb in the infrared, and it has different peaks in the infrared. And this is kind of a pain for us because when we try to do spectroscopy, try to do absorption measurements in the infrared, water gets in the way a lot, so it's hard to do. But you can look here, this is the absorption spectrum of the aorta, and this is the absorption spectrum of blood. So you can see things like pulse oximeter because you block it. These are just to show you some of the different types of lasers and where their wavelengths are. And this is one of the ones that can change wavelengths. But just to show you that depending on what you're trying to measure, you will get a laser to match the wavelengths that you're interested in. That's part of the reason why we have lasers of all these different wavelengths, okay, or LEDs of all these different wavelengths, because we try to match them with what we're trying to study. Now, why would we want to use a laser? Why is a laser important? What does the laser give us that some of the other light sources are? Coherent light, directionality.
And it can go on and off really fast.
Can go on and off really fast, so we can control the amount of energy deposited. Can be very bright, okay, and very monochromatic, single wavelengths. Those are some of the reasons. That's why we care about that. This is another way of looking at that diagram, but this one shows you melanosomes, whole blood, epidermis, aorta, and skin. It also shows you the absorbance of skin. So you see all of these things in a biological system lump on top of each other. So when I'm trying to do just sending light through my finger and trying to see how much light came through, I have to think about all those different species that get in the way. So if I want to measure blood, I have to pick the right wavelengths that there aren't a lot of other things that would confound my measurement. Ideally for diabetics, instead of having to prick their finger and put their blood inside of a little machine that then figures out how much sugar is in there, ideally we would just send light through their finger and figure it out. But there's so many other things in the way around where sugar absorbs light that makes that basically impossible. So we have to come up with other ways where there aren't those intervening species, like potentially measuring it by shining light in their eye, okay, or getting a sensor inside their skin. There's a lot of different ways that we can try to do this, and people have been trying for a long time because that would be a huge application that would be very, very welcomed by people that have to do that on a regular basis. So, as we talked about, there's not just absorption going on. I don't know if you guys remember this diagram from yesterday, but when light is absorbed, you can have things that relax vibrationally and lead to heat. You can have things that relax rotationally and potentially lead to heat. You can have this excited triple state and get relaxation by phosphorescence. You can get a vibrational and electronic transition that leads to fluorescence. So all these different things, absorption can lead to re-emission, can lead to fluorescence, can lead to making of the heat, feeling of heat, and can also lead to phosphorescence, the photons being left in some other way. So all of these things in biological systems are all happening simultaneously. Again, it's the amount in which they happen that matters and why we care about it. Okay, so now let's start talking about light coming from lasers, specifically interacting with tissue. What can those things do? So we can have thermal effects. That means we heat up biological things. We can have mechanical effects, which means we move things. We can have photoablative effects, which means that we basically vaporize stuff. It just goes poof into a little cloud. And we can have photodynamic effects, which means we cause some kind of change in chemical structure, which can lead to destruction of tumors and things of that sort. Okay? So, what are some of the processes that happen? You can have hyperthermia. Basically, you guys know that if you have a fever and the fever gets too high, you could die. Why is that? Why would having a really, really, really high fever potentially kill you? Yes? Because your proteins denature. The proteins fall apart. They can't do their job anymore. Then the DNA can also fall apart, though that would happen later. Okay? But you have a problem. You can't have the normal cell functions happening, and you can lead to death. Okay? So if you basically raise the temperature of cells to 41 to 44 degrees centigrade for some tens of minutes, you can basically kill a cell due to changes in its enzymatic capabilities. Okay? Now, it's difficult to do that, and it's a long time, so we don't use hyperthermia very, very much. Then we have coagulation. Leads to irreversible necrosis. Necrosis means cell death. Okay? Irreversible cell death. And what you're doing there is you reach a temperature somewhere between 50 and 100 centigrade for around a second. You basically dry out the cell. Okay? And you also denature proteins and collagen, and everything shrinks and the cell dies. Okay? That's one process that you can do. And then you have volatilization. The various constituents of tissue disappear in smoke at above 100 degrees centigrade. Literally poof. Okay? I'll show you later a little diagram that shows the poof happening. Okay? And you see the little vapors coming out. Now, if the volatilized region is narrow, well, this thing is just is narrow, a cutting effect is unobtained. So have you ever heard of a laser scalpel? Okay, that's what it's doing. It's coagulating. That's why they say, oh, the laser scalpel, you don't get bleeding, because it's cauterizing, it's coagulating all those proteins and sealing them shut as you're making the cut.
Is that making the cells explode up?
Is that what?
Is that also making the cells explode, or is it burning them?
Well, you're basically volatilizing them. So they're basically turning into vapor at that juncture. Okay, so you are destroying those cells, but you're causing this opening. Okay? So when we have a laser interacting with tissue, or really any kind of photons interacting with tissue, these are the things we care about. How much power per unit area are we delivering to the tissue? Okay? Because the more power per unit area, the more of a specific effect we're going to get. So this matters, but you need to know the wavelength and the amount of time that you're exposing the tissue to that light. Okay? Because you can adjust wavelength and you can adjust exposure time to get the desired effects. So what wavelength and exposure time and power per unit area do is they affect the temperature of the tissue. And the temperature of the tissue is going to tell you what's going to happen. Is the tissue just going to slowly die? The protein slowly denaturing? Is that happening quickly? Are you getting volatilization? Is the cell just going poof? You don't know. Okay? So you can change these things to affect the temperature, and you can change the time to also affect the temperature. Those are the things you have at your disposal. Okay? When you're developing a new system for doing something like removing your tattoos or shaving the cornea in your eye, you can control the wavelength, the exposure time, and the power per unit area, and that will affect the temperature of that tissue and what happens. Okay? So, here's a thermal effect. This is an unlucky graduate student who looked at an infrared laser a few too many times in their optical setup. Okay? And their eye, the back of their eye, where their rods and cones are, see these round spots here? That's where there are no more rods and cones. They went poof. Okay? They're gone. So the reason why we tell you not to stare at these lasers is because your eye is very good at focusing things, and it can take the intensity from the laser, further focus it in the back of the retina, increasing the density, the amount of power per unit area, and causing a loss of sensors there. Now, what does this look like to the person who has this? Well, they have a lot of holes in their vision. Now, we all already have one hole in our vision. You guys I'll bring you guys little things that you can find out where your blind spot is. Okay? The blind spot has to do with where the optic nerve goes back. But this person has 1, 2, 3, 4, 5, 6, 7, 8 additional blind spots. At some point, your brain doesn't compensate very well and you just have spots that you're missing, visioning. Now, why do we care? This is another example here, up here in this diagram. This thing is just dying. It shows you a whole bunch of burns. Now, you might say, well, why did this person get this? Well, they were working on an infrared laser. Infrared laser, can you see infrared light? No. The way they see infrared light is they take a little card, a specialized card, and they stick it in front of the beam, and it'll light up where the infrared laser beam is. But, they're sitting there adjusting hundreds of little mirrors, and oops, they got into the path of the beam, or the beam got deflected into their eye, and they just hear snap, crackle, pop, and they close their eyes, and all of a sudden, that happened to them. Okay? That's the problem. You hear snap, crackle, pop, which is your cells heating up, bursting, popping, okay? And then that's it. You don't really feel pain. You don't really have pain receptors back there, but you know something's really wrong, okay, when you open your eyes. They should have been wearing goggles. But, I just need to do this one little thing before I go to lunch, or I just got to run in and do this. Well, that's a problem. That's why at all of our labs, the doors lock, so you can't go in without somebody turning off the lasers. Lasers are on, they're locked, you have to know a special code, and you have to wear your goggles, that type of thing. Okay? Now, just to give you a sense, your eye has a focusing mechanism. If I take a regular light bulb, 100-watt light, okay, that's about a small one, but bright light, and I am 5 meters away from it, in my eye, the spot size that it will focus at is 300 to 400 micrometers. That's the size that this spot will focus on the back of my cornea. That leads to an irradiance, an amount of power of 150 watts per square meter. Okay, that's how much photonic energy basically is being deposited on the eye. If I do the same thing with a laser, 1 milliwatt lasers, and all the ones you guys use today are at least 5 milliwatts, okay? At least 5 times stronger than this. Then your eye still focuses the beam. The spot size becomes 2 micrometers. Notice much smaller than this spot size because it started out smaller, right? Than this. Now the irradiance is 300 million watts per square meter. So you've deposited a lot more power, and that's why you can cause damage. Fortunately, with a 1 milliwatt laser or a 5 milliwatt lasers, our eyes detect the light fast enough. They close the eyelid gets closed, and then you're okay. But some of those lasers from China that are not regulated to 5 milliwatts could cause problems because you might not react fast enough. Okay? So we had a researcher in CBST that was using lasers to coagulate, to stick together pieces of artery. So they could put sugar solution around the artery or some other material, heat it up with the laser, cause that stuff to coagulate, and it formed a seal. Okay, so that was another way that you can use the laser to seal 2 pieces together. Now, how does laser hair removal work? Okay, somehow what you're doing is you're taking advantage of the fact that all of you guys have different colored hair, but color absorbs energy. So what you do is you look for the melanin, which is the pigment responsible for hair color. You want it to absorb your laser's energy, and you want to convert that energy into heat. So if I want to do laser hair removal on you, then what I want to do is I want to concentrate a lot of heat into the base of the cell that generates that hair, and I want to kill it. I want to heat it and make it die, so therefore it can't grow the hair anymore. That's what laser hair removal is. Well, how do I do that? I have to pick the wavelength of the laser correctly so that your hair follicle will absorb that energy. I want to pulse it quickly. I want it to absorb it quickly. Just kill that cell, ideally, or just minimal damage with the cells around it, and then continue. Okay? And I want to do that over the whole area that you want to lose your hair on. Now, gosh, this thing is dead. Let's see. Now, if I want to do that, I need to control some different factors. I need to control how much power. I can control the wavelength. I can control the size of the beam. And this is just a readout from the machine that shows this is a machine here that does laser hair removal. And I can fine-tune it so that it actually deposits more or less energy. If you have darker hair, it's easier for that energy to be absorbed. If you have blonde hair, it's very hard. Laser hair removal is very hard for you because it's much harder for that hair to absorb the energy. As you guys well know, when you go outside and you're wearing a black t-shirt versus a white t-shirt and you go in the sun, the black t-shirt heats up a lot faster, right? So to deposit the energy into the hair follicle, it's much easier when you have dark hair. Now, I don't want to just turn the laser on and start going around your skin slowly. No, I want to pulse it because I want to give a quick pulse, deposit the energy in that spot, and I don't want a lot of time for the energy to diffuse into the surrounding cells and heat up all the surrounding cells. I just want to kill those follicle cells, okay, those initial cells that are responsible for the hair. So I do these fast pulses, and I hope that the majority of energy is deposited into your hair follicle rather than into the surrounding cells. Okay? And for the most part, if people know what they're doing, it works. In some states, it's not regulated, and anyone can buy one of these machines and say, put up a shingle, say we're going to do laser hair removal. So there were a lot of people that were getting some pretty nasty burns because people were adjusting, cranking up the power, making it longer time. Well, it leads to better hair removal. They weren't compensating for the fact that different people have different characteristics in their hair, and that was leading to burns. Okay? But again, you pulse a laser so that you can keep the follicle hot while the rest of the skin around it has time to cool. Okay? So that's how that process works. And with this process, I had actually sacrificed one hair for you guys, science, and I made a movie of it on my hand here. And this is the movie of it right here. Let me see if I can. What you'll notice is they first cool the area. They have a cold spot on there. And then they put it, that's the hair I wanted to remove. Do you guys see that little flash? And that's the hair and it's been fried. It's this little black spot over here. Okay? All the energy deposited in that hair and just fried the hair. Normally, I would have shaved first so that all the energy would go into the follicle rather than the length of the hair, because I want the energy to go into the follicle and kill that cell. But I wanted this hair to come back. So I just wanted it to show you the effect it has on the hair. Now, she cooled it first to minimize the damage to surrounding areas. And this is one for skin tightening and rejuvenation. You see all those flashes? You don't see those flashes when you're in the room. We only see those flashes because I had my digital camera, which is sensitive to near infrared. And guess what wavelengths they used? Near infrared wavelengths. So the camera would see the flashes, but my eye wouldn't. Okay? So that process is supposed to just slightly heat up the skin so that the collagen fibers realign and get rid of little minor wrinkles. Okay? So hair rejuvenation, skin rejuvenation, hair removal, skin rejuvenation, brown spot removal, spider veins, and more can all be done by this process. Okay, so we're out of time for today, but we will continue next time in creating shock waves.